First speaker is Chris Bilder from the University of Nebraska-Lincoln. And I know he has done quite a lot of work in group testing methodologies. The one time I actually went to Google, searched his name, I actually found a YouTube that he was and they're talking about these nice features of group testing. So she's going to talk about marginal regression models for multiple disease group testing data.
Well, welcome everyone. Thank you for coming to this session. Since I am doing the first talk here in this session on group testing, can everyone hear me? Okay, so I wasn't sure if this is on or not. Since I'm doing the first session, or the first talk in this session on group testing, I thought I'd give a little bit of a brief introduction to what group testing is. And this will also help put into context where my research falls in the grand scheme of things when it comes to group testing research. So let's consider a particular situation where we want to screen a large number of individuals for some kind of infectious disease. Maybe we're talking about HIV here, hepatitis C. And one way that we could go ahead and screen these individuals for the disease is to do what one would say is individual testing, where perhaps what we do is we get a blood specimen from every single individual, and so for this particular individual we get a blood specimen and we test it for the disease and we get a positive or negative test result. Then we go to the second individual, get a blood specimen and get a positive or negative test result. However, to do individual testing, unfortunately, it may not be feasible in some settings where you have a high volume of clinical specimens that have to be screened for a particular disease. Simply put, there's going to be a lot of tests that are involved, and so it might be very costly. It might also take a lot of time to do all the testing. So what's often done instead is group testing is used, also known as pool testing, where in this particular setting, what we can do is take these blood specimens and maybe pull them into groups of size 4 and get an overall positive or negative test response for this group or this pool. And if the group ends up being negative, then that says all 4, if one of these groups ends up being negative, that says all 4 individuals within the group are negative. So notice how it took just one test to determine that 4 people are negative for a disease, where with individual testing it took 4 tests to determine that 4 people are negative for a disease. Of course, though, a group could test positive. Then that says that there's at least one positive within the group. And depending upon the group testing application, it may or may not be of interest to determine, well, who in that group caused that positive group response. And if it is of interest, then there's a variety of what are called retesting strategies that can be used to determine, well, who the positive person or persons are. Now, the benefits then to using group testing is that you can have a very large reduction in the number of tests overall that are needed to screen a particular population. And if you're doing less tests, then you're going to probably observe some kind of cost savings as well. Now, this works out great, group testing does, if the overall disease prevalence is small. Because if the overall disease prevalence ends up being large, then you're in danger of most or even all groups testing positive. And so that if the actual determining who's positive and who's negative in a group is of interest, you may actually end up doing more tests through using group testing than what you would with individual testing. Now, group testing research is typically broken into 2 different areas. The first area is often referred to as the classification problem, where what you want to know is who's positive, who's negative within a positive testing group. This is going to be the subject of the other 2 talks in this session. What I'm going to focus on, though, is the estimation problem, where now what we're interested in is estimating, for example, the overall prevalence of a disease in a particular population, where what we may do is only observe the group responses themselves and not do any kind of retesting at all to determine who's positive and who's negative. And my particular talk is going to focus on a particular problem where we're interested in multiple diseases at the same time. And this occurs in a number of places in actual application. For example, with the American Red Cross, they need to screen blood donations for infectious diseases. They don't want to pass on a disease from a donor to a recipient. And they have to screen about 6 million blood donations per year for a wide variety of diseases. I think it's about 8 or 10 now. And in particular, when they screen for HIV, hepatitis B, and hepatitis C, they use one assay to get the result for the 3 different diseases. And they use groups of size 16 to actually do the testing. Back in my home state of Nebraska, the Nebraska Public Health Laboratory does a lot of chlamydia and gonorrhea screening. And in this particular setting, they end up having about 25,000 individuals per year that they need to screen for these diseases. And they use an assay that actually gives you both the chlamydia and gonorrhea result at the same time. Now, surprisingly, at least what I've been able to find, there's only one paper out there in the group testing literature that addresses this problem of testing for multiple diseases at the same time. This was a Biometrica 2000 paper by Hughes, Oliver, and Rosenberger. And what they were interested in doing was estimating the overall prevalence of the actual disease or diseases, I should say. And they assumed that there's perfect diagnostic tests in their actual screening. Just a second, my computer's thinking here. So what I want to do is continue my talk and discuss group testing regression models for multiple disease screening data. So no longer am I interested in just the overall prevalence that was already done before. What I'm interested in is, given particular risk factors, or let's say covariates, I want to estimate the probability a particular person has a disease, or positive for even something else that group testing is used for. And what I'm going to do is assume that I have, or not necessarily assume, I'm going to generalize to the case where I have imperfect diagnostic tests. So now we have a sensitivity, a specificity. They're not necessarily equal to 1 for a particular test. What this ends up being then is actually just a correlated binary data problem. But the unique aspect of it is this, and that is, if I just observe the group responses themselves, the actual individual responses, whether or not an individual is positive or negative for a disease, that's unknown. So what we have here is a set of unobserved, correlated binary random variables that we are interested in working with. Okay, so let's do some notation here. I'm going to let Y tilde be the true unknown individual status, where the subscript there, the J corresponds to the disease of interest, where there's capital J different diseases. I corresponds to the individual, and K corresponds to the particular group, where there's capital K groups and capital I sub K individuals within each group. These Y tildes are binary, 0 for a negative, 1 for a positive response, and they're likely to be correlated across the different diseases for a particular individual. What we're interested in doing then is looking at this right here. The probability of having a positive individual for a particular disease given a set of risk factors denoted by my covariates. And we're going to denote this probability as P tilde, sub ijk. So that then my model, then we could simply work with a logit model here in this particular situation, where we have the logit of P tilde sub ijk is equal to then the linear combination of my covariates with a set of parameters or betas that we want to estimate. Notice here on these parameters I have a subscript J that corresponds to the particular disease. Again, in this particular setting, though, that these Y tildes are not observed, and that's what makes this problem more statistically interesting. What we do observe, though, are the group responses. I'm going to denote the group responses as Z's. So Z sub jk is my observable test group response for disease J of group K. These z's are binary as well then, and of course they're going to be likely correlated across the different diseases. We'll let theta sub jk be then the probability of a positive test response. Now these z's are the test responses themselves. They are subject to testing error. So then we need to define, well, what the true group responses would be, and simply we'll call them z tildes. We'll let then eta sub j be the corresponding sensitivity, and delta sub j be the corresponding specificity of the test. Then to actually then estimate then these probabilities on the individual scale, these p tildes, I need to establish some kind of relationship between the group test probabilities and the individual probabilities. And simply this is what it looks like, where we have the probability of a group test response being positive is equal to sensitivity times the probability that the group is truly positive plus 1 minus specificity times then the probability that the group is truly negative. And we can find these probabilities of the true group responses in terms of the true individual responses as shown there. So now we have this relationship. Once we have that, then we can talk about, well, how can I actually then estimate our parameters in our model? Well, this is where the expectation solution, or ES algorithm, comes in. That was proposed by Lassoff and Ryan in 2004. And for our purposes here, we can think of it as a generalization of GEE methodology and the EM algorithm. The reason why this is important is because in terms of GE methodology is often used for modeling correlated binary data, which is what we have. The EM algorithm is often used in situations where we have some unobserved response, and so we have to use an expected value given the information that we do observe. Well, that's exactly what we're going to do here to estimate our model. So let's first of all just write then a set of generalized estimating equations in terms of these y tildes, which again we do not observe. And this is the usual form that we would see for a set of generalized estimating equations. I know there's a lot of notation here, but again, just think of it as the usual form. Specifically here, we have a vector of these y tildes for a particular individual in a particular group. So this is a j by 1 vector. We have their corresponding probabilities of being positive listed there. We also have a working correlation matrix that we're going to have to worry about too, R sub alpha. And alpha is just a set of parameters, working correlations that we need to estimate somehow. And generally in a generalized estimating equation situation, what you're interested in doing is solving the estimating equation then for your vector beta, your regression parameters. Again, y tilde is not observed. So what can we do? And this is where the ES algorithm comes in. What we can do is then perform the E step, where we're going to replace these y tildes with the expected value of y tilde given the information we do observe from the groups. Now, fortunately, there's nice little closed form expressions then for these expected values, conditional on do I have a positive or negative group response. Where, for example, if we focus on this first expected value here, we can see that in the denominator, I have simply the probability of a positive group response. In the numerator, I have the sensitivity and also the individual probability. Now, what happens if you have other kinds of group testing protocols where you not only do you maybe observe the initial group responses, but maybe also observe retests? I will discuss how to handle those situations at the end of my talk, and basically it just involves a modification of these expected values. So once we got these expected values, then we simply put these expected values in our set of generalized estimating equations where we had a y sub ik before. Now we have, let's call it an omega sub ik, these expected values. And we solve for the vector of parameters, regression parameters, our betas. That's the S step, or solution step. And what we can do is simply iterate between the E and S steps until convergence. Well, what about estimating this working correlation matrix in this particular setting? And this is where it's not, let's say, a direct application of the ES algorithm itself. So what I would like to do is somehow come up with an estimate then for these what I call individual correlations, the correlation between the individual response for disease J and J prime. We can denote it simply by alpha sub JJ prime. Well, what one can end up showing is this, that the covariance for the group responses for disease J and J prime is actually a polynomial function of these individual correlations. Polynomial of order I sub k. Once I have that, then I have established a relationship between something I don't know and something that I could maybe perhaps estimate, and then eventually then solve for the estimate for these alphas. I don't have time to go into the actual proof involved with this, with showing this. Uh-oh. I apologize with problems with my computer. Okay, so what we've just shown, to recap, is a relationship between the covariance of the group responses and the correlation amongst the individual responses. And what this does, it provides us a way to then estimate then this working correlation, and simply using a method of moment estimator. So let's let R sub jk basically denote residuals, where we take the group response minus this estimated probability of being positive for the group response. And then simply what we have here is basically the expression that we just saw on the previous slide, except for now on the left-hand side of my equality here, I replace it with a corresponding estimator. I sum over the groups. I also put some hats on top of the p tildes here. And so now what I can do is solve for the alpha sub jj prime, and I got my estimate of my working correlation matrix. In the end, one can prove that there is one unique solution and the estimator is consistent. So that's good. But the fact that this is potentially a large order polynomial that you have to work with can make this somewhat time consuming. And so what we also investigated was, well, is there a way that we can maybe make this simpler? And in fact, this polynomial, the higher order coefficients of the polynomial are almost always very, very close to zero. The reason being is because these individual probabilities of being positive for a disease, generally speaking, are often quite small. And so what one can end up doing is just working with the higher order coefficients. I'm sorry, one can work with just the first and second order coefficients of this polynomial and then come up with an estimate for the working correlation that way. And in the end, you get very large time savings. For example, we investigated some particular settings where if you have a group size of 10, the time that it takes to estimate the model is reduced by 80% if you use just the linear and quadratic terms. And you really don't lose anything in the end. Our vector or parameter estimates are asymptotically normal, just follows from a Lashoff and Ryan. We end up using a sandwich estimator for the estimated covariance, and we can use wall-based inference procedures with it. So let's take a look at some simulations then to evaluate how well this procedure works in a finite sampling situation, or a fixed sample size situation. In this particular setting, we're going to work with a simple logit model where we have two diseases. We're going to have two covariates. One has a uniform distribution, one has a gamma distribution. We have a set of betas also that we're going to be working with. And the main purpose then of these betas and these the distributions for the x's is so that we have a very low prevalence overall. So for disease 1, we have a 3% prevalence, and for disease 2, we have approximately a 2% overall prevalence, which is common in group testing settings. We end up using a correlated binary data generation algorithm to simulate our data, and we just adapted a little bit for the context of group testing. Sensitivity and specificity of 0.95. We'll use B equal 1,000 simulated data sets. Okay, so here's a table showing some of our simulation results. If you notice in the first column here, we have values of our correlation. Second column, values of the number of groups we have. And third column corresponds to the group size. So overall, we have 10,000 individuals always fixed. We have such a large number there because that's what we often see in at least the group testing applications that we work with. And if we focus in on the mean row, what we have summarized here is basically, I just simply average my beta hats over the 1,000 simulated data sets. And the purpose is to show that indeed that these average values are very close to what you would what you hope for in terms of the true parameter values. So that's a good result to have. Then in the next row, this SE/SD row, basically what we do is we average over the standard errors that come about through our sandwich covariance matrix estimate. And we take that divided by then the standard deviation of all the beta hats. What we're hoping for here is that we get a value that's close to 1. And indeed, that's what we're getting. So that's a good sign as well. And lastly here, we also look at coverage for 95% walled confidence intervals. And you can see that those values are just about 95%. So this helps validate that indeed that our approach in a fixed sample size setting is indeed working. Let's take a look at an application then of this methodology. This is going back to the chlamydia and gonorrhea screening in Nebraska. And these are important. These diseases are important in Nebraska because they've been characterized as being at epidemic levels in Omaha. And the screening in Nebraska is done as part of the CDC's infertility prevention project. This is a nationally implemented program. Every state participates in it. And the purpose of the program is to assess and then hopefully reduce the prevalence of gonorrhea and chlamydia in our population. In Nebraska, there are about 25,000 tests done annually per year. The specimens are taken at various health clinics around the state, and they're shipped to Omaha, where the Nebraska Public Health Laboratory is, and that's where the actual testing is done. The assay that's used for the tests for both diseases at the same time. And, these tests aren't cheap. $11 for a swab test, $16 for a urine test. So, they're spending at least $300,000 per year. And in case I failed to mention this, they're actually doing individual testing right now. They're not using group testing. Well, other places or other public health labs that participate in this infertility prevention project have also seen these large costs. And they've started using group testing. I think at most I've seen so far in my count, there might be about 8 public labs that are actually doing this now. And the NPHL in Nebraska is interested in doing group testing. Where the primary goal then for this particular setting is classification, because they want to know who's positive and who's negative for the disease. However, also in this setting, we have a rich set of risk factors that we collect information on, in addition to actually collecting specimens from the individuals. So it would make sense then to also examine the estimation settings so you can get a better grasp at how bad this problem is and what factors affect positive or negative status. And so that's what we're going to talk about here, is the estimation problem. We're going to just focus on about the 14,500 female swab specimens that were screened in 2009. These tests aren't perfect. Sensitivities and specificities range from about 0.928 to 0.98. And since what we have is actual individual testing data, what we're going to do is actually artificially form groups of size 5 by testing data. This is typically how it will be done in practice. As specimens come in, you're going to form the groups. What we're going to do is form positive group responses by if any individual within the group tested positive, that's going to be a positive group response. If all individuals were negative, then that's going to be a negative group response. Note that this does not take into account the fact that there is testing error, though. But there's not necessarily a good way that's perfect to take individual testing data and make it into group testing data. So the covariates that we have access to are age, race, was someone actually experiencing symptoms when they came in, various clinical observations that are made while they're at the health clinic, and also self-reported risk history as well, given when they were at the health clinic. All covariates are binary except for age. And we're just simply going to consider this logit model where we have linear terms for our covariates. If we use a second order approximation to estimate this working correlation, we get about 0.27. And then for comparison purposes, and this is why we want to work with individual testing data as well, is that we are going to fit a model using conventional GE methodology. We're going to fit it to the individual responses so that we have some way of comparing to see how would we do with group testing and compared to individual testing. Unfortunately, though, we weren't able to actually incorporate the testing error into the actual estimation due to some problems with non-convergence. I won't get into the exact details here, but it just has to deal with the fact that the specificity is low enough relative to the actual prevalence for gonorrhea that's causing this non-convergence. Okay, so here's a table of our parameter estimates, and yes, there are a lot of them here. We have them broken up into by disease and also by the corresponding covariate. We have estimates from the ES algorithm and estimates from using GEE with the individuals. So we have estimates, standard errors, p-values from wall tests, testing whether or not the parameter is equal to 0 or not. We combine all the race levels together to form one test. That's why you see some empty spaces there in the table. And what you can see from looking at these p-values is that we're getting somewhat similar results in terms of which ones are significant at the 0.05 level. Those are the ones colored in orange there. We do see some differences, but that's not necessarily a cause for concern because this GEE model is using individual testing data. So you have 5 times the number of actual responses with the GE approach than what you do with the ES algorithm. Also, some other comparisons. These parameter estimates generally are similar for the two methods. Standard errors are lower for GE, again, not surprising. But what's interesting is that these group testing standard errors are only 1.3 to 3 times larger than the individual testing standard errors, even though we have 5 times more observations with the GEE approach. Now, one could also do some other kind of testing with this particular model. In particular, what you could do is examine the regression parameters across the different diseases for the exact same covariates. That's why I have a subscript R there to indicate same covariate, but just different diseases. And what this is going to allow you to do is examine how a covariate affects both diseases. Is the effect similar or is it different? And without going into all the details, p-values were less than 0.05 for all the terms in our model except for these 4 particular ones. And if perhaps a simpler model was desirable, one perhaps could explore sharing parameters then across diseases for some of these non-significant sets of parameters. So, in summary then, we've talked about group testing regression models for multiple disease data. The reason why I really like this approach is that it allows you to model the data as it naturally arises in application, where you have multiple diseases tested for at the same time. We plan to include R functions that will fit these models in our bin group package sometime in the near future. What about if we did have retests? So in some situations, again, you're interested in actually decoding the positives from the negatives. Well, if you had that extra information, you also wanted to do estimation, how would you do it using the methodology I just presented? Well, there's basically 2 changes to what we would do. First, we just changed this expected value that we were using before in the E step of the ES algorithm. We changed it now to be conditional on the observed tests and all the retests. There are sometimes closed form solutions, depending upon the group testing protocol. Other times, there are not closed form solutions, and you actually have to use simulation techniques to actually estimate these expected values. Second, we need to estimate this working correlation structure. You could still use just the initial group responses themselves to do it. But you would think that you would gain information from actually taking into account the retest. And how exactly to do that yet we haven't quite worked out, and that will be the subject of future research. Lastly then, you can also use these models in a longitudinal setting, where let's say that now we just have one disease and we do group testing over time in a longitudinal setting. Now the J subscript in my notation before, which denoted disease, now corresponds to the jth time point. There is one little restriction, though, and that is the same individuals using our methodology will always need to be pulled together. In the end, it becomes, you have a lot more stuff that's correlated if you allow individuals to be in different pools, and so it becomes a lot more messier, and that's something to consider for future research as well. Okay, so sorry for the little problems with my computer there, but that is the end of my talk. Are there any questions?